All right. Hey, everybody. So today I was going to do a quick overview of the code that we have in our JIT repo as of today is 3/6. And so today it's Friday, and I'll mention this video in class today. So looking at our VM and making sure I'm in the correct location. So our JIT repo, CPSC 3600-students, and we see all the usual things. One thing that is new, so there's a docs directory, and the only thing I have in there now is basically an overview of what's in this video that you're currently watching, and these were more notes for me to make sure I talk about sort of a small number of items and don't stray too far. So we'll take a quick walk through the code directories. Some of this is review, but there is a new code directory or subdirectory, and that's the solution for the UDPEcho program from homework 2. Let's see, so I'm gonna step into the very first program that we looked at, CPPEX1. Want to talk quickly about the scripts that were used. I've not really said much about bash scripting, but I'll provide a little bit of insight. Also, in one of the code projects, UDPEcho version 2, just going to illustrate how one might use the Unix program diff, which is super useful. Super complicated. You can it does a whole bunch of things, but I'll be showing you a couple of ways to use it. Then the new version of UDPEcho, which reflects the homework 2 solution, is UDPEcho version 3. Let's see, I will be running that from my VM, and I'm located at home right now, and I'll put the server on a school computing machine, and we'll go through the process of how do you package that program and SFTP it to a different location. Note that in order to run that program on a school computing machine, when I'm remote, I need to be VPN'd into Clemson. And so let me just make sure that everyone is clear on what I mean by that. So let's see, my platform is unfortunately Windows, but if you go to the CCIT, there's software library where you can download stuff. One of the things that you can get is called Cisco AnyConnect, and basically this is a VPN client, and so you would install it on your laptop. So VPN stands for Virtual Private Network. It basically provides a secure tunnel from your host to Clemson's network. So it is effectively as if we have for example, an Ethernet connection someplace on campus. In reality, we're going through the public internet to get there, but the VPN provides a secure way of providing a sort of a virtual Ethernet connection to campus. So with that, I can directly SSH into any machine on campus from my VM. Let's see. Okay, and then the final thing, I'll talk again about some of these useful Unix commands. Probably saying a few words about the find command, which again is super, super helpful. Okay, and I'm trying to keep this video 15 minutes or less, so let's get started. First step is do this with me. I think that would be the best way to view this. So on your laptop, you can view the video, and if you want to pause the video, or actually I'll give you a few minutes here to do the following. So do a JIT update. Like that, and that should give you the latest code. And then go ahead and step into docs and read over I can't type. Read over this, and I'll give you a minute to get to that point. And I apologize, you might hear my dog in the background. All right. So let's start out by demonstrating diff. Okay, so in code, we have a new version of UDPEcho, so UDPEcho version 3. And when I see new code that's based on prior code, the first thing I'm interested in is finding out what has changed. And there's different ways to do this. JIT has commands to diff files and look at differences. I just wanted to point out the standard diff Unix command, because there's a couple ways that I use diff pretty much every day. And so if we do a man diff, the -Q option is helpful. So that's what we're going to use. So we're going to use -Q, which basically is just going to identify files that differ. So we want to do it diff-Q of the contents of this directory. So this would be the new, so UDPEcho version 3, and we want to see what's different from the old UDPEcho version 2. It's going to probably give us a lot of information, so I'm going to pipe that to more. Actually, I'll use less, so more is perfectly fine. It's in this case, it really doesn't matter because it's just giving us a page of output. So, but in general, I actually prefer less over more. Okay, that's super confusing, but the two programs are equivalent. Less just lets you do more. Okay, again, they called it less for a purpose. They're Unix people try to be funny. All right, so the output is telling us, if you could follow my cursor. So first of all, .o files we can ignore because, all right, you know, they're going to build most likely differently. Let's just pay attention to changes in source. So .c, client.c is different. So in our current directory, common.h is a new file. Okay, the make file has changed. The readme file has changed. Server.c has changed. And session, there's some new files. Session.c, session.h, and the session manager, that shouldn't be there. So I'm actually going to remove those. Let's see, towards the end of the page, it's saying that UDPEcho.h has changed, utils.c and .h have changed. So pretty much all the source has changed. The modifications are fairly straightforward. But first, let me remove the session manager stuff because that was actually old code, and the new code to support session manager is in session.c. So that gets us to the major change in version 3 is the server is now able to maintain statistics on a per client basis. So we call each of those interactions with a particular client a session. So let's first, oops. As always, with new code, do a make clean, do a make all. Pretty much with all the code that you see from me, you'll always be seeing these warnings, which are indicating that there's a type mismatch, usually in a printf, where the mismatch is between an int and a long int. And this is because of 32 versus 64 bit platform differences, and let's for now just ignore those. We could actually turn off that warning if we add into the make.defines at the commands that reflect the parameters to the compilers. We're going to say -w format equals, which is going to tell it to don't show us those warnings. But I actually like to keep it on because there's certain format warnings which will lead to problems. So for example, keep your eyes open for one of these warnings where the mismatch is a like a %d, but the actual type of the argument is, for example, a string, or vice versa. So a %s and the actual argument is perhaps a double or an int. You'll likely see it'll compile, it'll give you a warning, but you'll likely see a seg fault in your program. Okay. So if you do a question mark, you'll get the usage. We're going to run the server. We're going to select port 5000, and we're going to say debug level. It could be either 0 or 1. 0 is not going to show each iteration, but it'll show final stats. A 1 will show each iteration. So at the client, we're going to say localhost port 5000, iteration delay, I'll say, again, this is in microseconds, so I'll say 0.1 second, message size of 100 bytes, another number of iterations 10, debug level 1. Okay, and so the client completes, it shows each of the 10 iterations. Actually, I guess it's off by 1. And the final line there is the summary stats. So let me get another window open here. If we look at the client, so we want to find out what exactly are the fields that are being displayed. Let's start with the stats. At the end of the program, so when a Control-C is entered, that causes the system to issue a SIGINT signal, and we've registered client Control-C code, this routine, as our handler, so it gets called. We call final stats, which is a routine whose job is to basically compute the final stats. One thing that's new in this version, so it calls a routine called send session close signal, and we'll look at that code here in a second, but conceptually it's very simple. So we want to be able to have the client tell the server the session is over, okay? Otherwise the client is not going to know that. And if the client is dealing with millions of, or if the server is dealing with millions of clients, it's easier for the server to be able to clean up after a closed session. It doesn't have to have as much state open. So it's more efficient in memory usage. So the signal, the way we're going to indicate to the server the client session is complete is we're going to send a sequence number of all ones. Okay, so again, in the world of networking, all ones typically has special meaning, and we talked about that in the context of addresses, right? So all ones typically is broadcasts. We're going to say that a sequence number of all ones has special meaning. It is telling the server this session is over. That says that our client can never, if it runs for a long time, the sequence number, which is a unsigned 32-bit int, is going to keep being incremented with each new message. And if it runs for a long time, eventually it's going to reach the max unsigned int value, which is all ones. And so we need to make sure that the client code does not do that. And that's called looking for a wrap of the sequence number. And we'll look at the code required to do that. But this is all just additional complexity for a very simple thing. We want the client to be able to convey to the server the session is over. So when we hit a Control-C at the client, this routine is going to be called. The first thing it does is it's going to send a message with that signal, with that sequence number, all ones. And then this is most likely not necessary, just delays for 10 microseconds. We're then going to compute the average round trip time, our best guess as to the number of packets lost, and we can compute the average loss rate by dividing the total number of packets lost by the total number of iterations, number of trials. And so what we print out is in this printf. So that this very bottom line here is coming from this printf. First field is the wall clock time. Duration is the amount of time the session ran. So it's the number there is 0.92 seconds. The average round trip time observed was 0.0004. The average loss rate was 0.1. And something tells me that the way that the client is terminating, it's always going to be off by 1. So the send count is always going to be greater than the count of messages returned, which is an error. Okay, so, but that's why we're seeing an average loss rate of 0.1 in this case. I'll actually fix that problem before I release this code in the JIT repo. Okay, and then number of trials. Received count, number of RTT samples, number lost, RX error count, TX error count, number of out of orders. And all of those are fairly uninteresting in this run. We do detect one loss, and again, I think that's just due to a minor coding problem on my part, which I'll fix. Okay, the information shown each iteration. Let's look at that. All right, so I'm using VI. Oops. Okay, and to find out where the executable is, I do which. If I do an ls-lt/user bin vi, we'll see that it's actually linked to /etc alternatives vi, which is most likely vim, which is sort of the modern version of vi. Okay, so this link, this is exactly what we've seen in some of our code examples. I use symbolic links frequently. They're super helpful. And so that the command is ln to link, to do a symbolic link, we would issue an ln-s target name link name. So to create this link for VI, that there's a script somewhere that would have done ln-s target name and link name. So the target name would be the VI, and then the link name would be /etc/alternatives/vi. Oh, sorry, I got that backwards. The target name would be /etc/alternatives/vi. That's the real program we want to use. The link name is when we type vi, our paths are set up to pick it up in user bin, but this is going to point to this. And so we're going to end up using this version of the program. Okay, hopefully that was somewhat not confusing. All right, so in the client code, so remember that parameter to the client. The last one was the debug level 0 or 1. 0, we're not going to show per iteration results. If it's 1, this is what we're going to show. And so each line is an iteration. First field is the wall clock. Second field is going to be the round trip time sample, RTT sample. The third is something called the smoothed RTT. So basically what we're doing is we're maintaining a sort of a moving average of round trip time samples. And I point this out only because if we were to use the round trip time samples in this code in some meaningful way, we most likely wouldn't want to use or make decisions based on a single round trip time sample, because in the internet it's highly variable. There could be random delays at any time, and we might only see it on one packet, and then the next packet we don't see it. And so it's really important to filter or smooth out many of the measurements that we get from a network. And this is one method of maintaining a basically an average in real time. So it doesn't require, a large number of round trip time samples, and we compute the mean by summing and dividing by that number. This is an alternative method to doing that. Okay, and then the other information shown other than the smoothed RTT, receive count, and number of samples. So we have the time, the wall clock time, round trip time, sample, smoothed round trip time, and then the number received and number of samples. Okay, so we started the server, we ran the client once. The server we ran with a debug level of 1, so it's showing per iteration numbers, wall clock time, size of the message, which is 100 bytes, sequence number. This next field is the server's maintaining the largest sequence number seen. And let's look at the code to see what that next field is. So to see that printf that produces the per iteration information, you could search. So in VI, if you do just hit / and then type something, and it'll search and put you in the file where it finds it. So I'm going to search for debug level. Okay, so if debug level is 1, so the information that is shown is the wall clock time, number of bytes received in the message, the sequence number contained in the message, something called the actual sequence number, and the largest sequence number seen so far for that session. And then something called OWD sample, one-way delay sample. So another change to this code from the delta from version 2 to version 3 is when we receive a message from the client, here's the top of our while loop, and about the first thing that we do is we do a receive from. And so again, this is the server. The first thing it's going to do is enter the loop, do a receive from. It's going to block waiting for a client. When a client sends a message, the client's address is going to be put into this struct client, which is a sock adder. And num bytes received is going to be either -1 on error, potentially 0, which would not make sense to me in this program. So I think I flag it as an error. Actually, I flag if number of bytes received less than message min, which I've defined to be 12 bytes, which reflect the 3 uint32 fields or numbers that must be in the message. In other words, it's the message header. Coming off the receive from, so the data is going to be in buffer. And so this is our trick of how we unpack the network buffer. So the data from the IP datagram, it has been transferred into our buffer called buffer, and we want to pull from that buffer the specific typed data as a series of unsigned ints, and put those numbers into a structure called a message header, just to make it easier for us to then do something with. So we use a pointer that is going to be of type pointer to an unsigned int, and we set that to the top of the buffer. We're going to, this line is saying, using that address, step into it. So give me the contents of of what that pointer is pointing to at that address location in units of an unsigned 32-bit int, and n2 host long will order those 4 octets in the correct network byte order so that they're placed into our header struct field in the correct host byte order. So sequence number for the very first iteration should be the value 1, and it's incremented each time. A part of that operation, that copy from the network buffer into the message header sequence number, is a post increment of the pointer, and C will handle incrementing it by the right amount. In other words, since it's a pointer to a uint32, C will know to increment by 4. So the next time we do this, the pointer has been incremented to the correct location in the network buffer, and now we read, or we copy, the next field of interest, which is going to be the first part of the time spec, which would be the seconds, and then the next is going to be the nanoseconds. And again, those two define the wall clock time at the client when it sent this message. Okay, so let's call that T0. We obtain a wall clock time in this call, get current time D. Let's call this T1. Okay, and so the time it took to send that message from the client to the server would be T1 this time minus T0, which would be the time that we learned the client, at which the client sent the message. And let's take a look at that calculation. So the one-way delay sample is going to be wall time minus okay, so we're doing a couple of things here. We're basically creating or transforming the two fields of the time, so the seconds plus the nanoseconds, transforming it into a double. And that is why we do the divide by 1 billion. It's because we need to take this number, which represents nanoseconds, and divide it by effectively 1 billion to have it become, seconds dot whatever that number is. So it's the precision of the one-way delay sample in nanosecond precision. At the end of the program, well, we're monitoring to be able to compute the average one-way delay. So we sum all samples and have a counter that indicates how many samples. All right, and so let me talk about this actual sequence number. So again, you could assume it's effectively the sequence number that comes in off the client message. So it's the sequence number, the most recent sequence number. What the code tries to do here, which I probably shouldn't have added because it makes it more difficult to understand, but dealing with wrapping is sort of a big issue. And so this shows how we deal with it. So the sequence number is that's passed in the message is a uint32. So the maximum size is 4.2 billion something, which is a large number. And for all of our use cases, we'll never wrap the sequence number. If we were to wrap, so we have code elsewhere that is going to count the number of times that we wrap. That's sequence number wrap. And uint max is basically a system define that gives the maximum value of a uint32 type integer, which is that 4.2 billion something. So our actual sequence number is going to be the sequence number that came in, plus if we wrapped, we have to add the amount that represents the uint max times the number of times we wrapped. This allows this program to run forever. Okay, let's talk about the session support. All right, so the easiest way to do that is let's look at the README file. Okay, so in two new files, session.c, session.h. In session.h, we define this large struct called a session. This contains the state associated with a session that we want to maintain. Some of these fields we don't have to talk about, okay? I'll only mention the main ones now. So when we create, the first time a new client sends a message, we create a new struct. Okay, so that means that this struct is a doubly linked list, which means it has a forward and backwards pointer to elements in the list. Okay. The second most important thing to note here is the session has to have the basic information that uniquely defines the client session. And we will use the client IP address and the client port. Okay, other things that we pay attention to, we note the time at which the session starts. we note, so first arrival time is the time, effectively the time the session starts, the very first message received, the new message received. And as messages are received, we always update last arrival time so that we have the time at which this session was last active. And then we maintain byte counts. We track sequence numbers, the last sequence number, the largest sequence number seen. Some of these aren't relevant for this particular application, but like largest sequence number sent, so that would be the when the server issues a reply, it's going to record the sequence number. It should always be the largest sequence number received for this particular program. When we talk about window protocols in our transport protocol discussion, we'll see why some of these numbers, variables might be different. We're also going to try to track the jitter associated with the arrivals. So, the client sends messages at a periodic rate, and jitter is a standard networking measurement that effectively helps us describe the variability in the period of the client's sending process. So it's, if the client is supposed to send a packet at every 1 second, the jitter is going to tell us the statistical range of variation associated with that that periodic target. So it's we're interested in the mean of the arrival times or inter-arrival times. So we want to measure, if the client is trying to send every 1 second, where the server side is actually going to be observing the arrival time and the distance, or the time between arrivals, called the inter-arrival time. So it'll be able to compute the average inter-arrival time, which will be sort of close to the, in our example, 1 second. The jitter helps us determine it's actually related to the distribution of variation. And instead of, we could plot the probability distribution based on measurement of the inter-arrival time, the jitter gives us a single number that is somewhat meaningful, as is the variation, standard deviation of statistics that we also do calculate. Okay, so the session.h, this gives us a glimpse of the routines that we use. Find active, so when the server receives a message from a client, it calls find active, and this routine is either going to return a pointer to the session, or it will return a pointer to a session, and it could be an established session, or if find active doesn't find a match, it would create a new session and add it into the linked list and fill in the information. All right. Let's see. I'm not going to talk about these other ones yet. When we're all done with the server program, for example, we issue a Control-C, it calls print sessions, which is going to step through all sessions and give summary statistics of each session. All right, so in the server main program, current session is going to be the base pointer to the linked list. And we're at the location in the server code where it's received a message and it's done some validation and everything looks good. Calls get active and we get a pointer to the session associated with this client. Do a couple of error checks. Compute the actual sequence number, one-way delay sample. We show the per iteration output, and okay, then we continue sort of filling in session information. So if this was the first message from a new client, so it's a new session, we discover that by the first arrival time is going to be -1. So the routine find active session does not fill in all session information. This code fills in actually most of the information. So this would be the first time, and then the else would be, okay, this is an established session, so we're going to set fields like the current jitter sample, arrival time. We're taking, we will eventually want the average of the jitter, so we're summing all samples. We also want the average inner arrival time, so we're summing all samples. We are counting the number of bytes received, the number of messages, and this is our method by which we attempt to detect loss. So the term is we're looking for gaps in the sequence number. So as an example, if the last message was sequence number 101, and then all of a sudden we receive 105, that would suggest that 102, 103, and 104 were dropped. And so the actual sequence number in this example would be 101 minus the last, the actual sequence number would be 105. The last sequence number would be 101. So that difference is 4, and need to decrement by 1 to make things correct. And so temp y is going to be equal to 3. We're interested in finding the, well, let's see, finding the average one-way delays. So we count. The one-way delay can actually be positive or negative. The accuracy of the one-way delay totally depends on if the two hosts, if their wall clock time is synced. And When we run on localhost, it is. When we're running on normal computers, it typically is not. Okay, so I think I'll end this part of the discussion. Let's go back to the script. So I'm doing things a little bit out of order. All right, so all right, so I see that this took a lot longer than what I was planning on doing. I'm going to end this video now. We'll call this a video that introduces you to the UDPEcho version 3 program, and we'll talk more about it in class. I'll have an additional video that does some of the other things that I mentioned in our list. Like in particular, I wanted to go back into CPPEX1 and talk a little bit about the scripts. So this script simply calls another script, an EXP. This is a very typical script you might come across, and I'll basically just step through or introduce you to the syntax associated with bash, which might be helpful in future scripts that we come across in class. So with that, I will say goodbye and see you in class.